Imagine a civilization 1 million years older than ours. They have telescopes we cannot dream of. They have mapped every rocky world within 1,000 light years of their sun. They know Earth exists. They know it has oceans, oxygen, and cities glowing on the night side. They have seen us. And still, they have never come. Not because they do not want to, not because some cosmic law forbids them, because between their star and ours lies a distance so vast, an energy cost so extreme, and a hazard so unforgiving that even a civilization capable of noticing us may be permanently unable to reach us. Tonight, we are walking through why the galaxy may be full of eyes that see each other and hands that can never truly touch. If the quiet corners of space are the kind of thing you enjoy exploring, a like and a subscribe genuinely helps this channel grow. Also, before we begin, we are now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. There is an idea that lives quietly in the back of almost every human mind that has ever looked up at the night sky and wondered whether we are alone. It is not usually stated out loud. It is not written into textbooks. It is more of a feeling, a background assumption that shapes how we imagine the future of the cosmos and our place inside it. The assumption goes something like this. If a civilization becomes advanced enough, truly advanced, not just a little further along than us, but hundreds of thousands or millions of years further along, then eventually, inevitably, they will come here. They will build their ships, they will cross the dark, they will arrive. It feels almost obvious. It shows up everywhere in how we talk about aliens. When someone asks, well, if they exist, where are they? The unspoken half of that question is always the same. Where are they? Meaning, why are they not here yet? Existence and arrival are treated as the same problem, separated only by time. Tonight, I want to sit with you and carefully take that assumption apart, not to mock it, not to dismiss it, but to show you what it hides. Because when you look at the physics, being an advanced civilization and showing up at Earth are not the same achievement. They live on different sides of a chasm so wide that intelligence itself might not be enough to cross it. To see why, we have to start with the distinction that almost nobody makes when they think about alien contact. Reaching Earth is not one thing. It is 4 things. 4 separate achievements, stacked one on top of the other, each one dramatically harder than the last. And most people, when they imagine an advanced civilization, quietly assume that all 4 come as a package, that if you can do the first, you can do the 4th. That intelligence is a ladder where every rung is roughly the same height. It is not. The rungs get exponentially further apart the higher you climb. Let me lay out the 4 achievements before we go deeper. The first is detecting Earth. Simply noticing that we exist. Recognizing that this pale, small, bluish dot orbiting an unremarkable yellow star has water, has oxygen, has weather, has structure. The second is sending a signal. Choosing to aim a beam of radio waves or laser pulses in our direction, so that we might, if we were listening at the right moment on the right frequency, hear that someone else is out there. The third is sending a probe. A physical object, a piece of matter, a machine, a robot, a chunk of engineered substance that crosses the interstellar gulf and arrives at our solar system intact. The fourth, and this is the one almost every science fiction story quietly assumes is normal, is sending living travelers, beings, bodies, minds inside biological or perhaps post-biological substrates that step out of a ship, look around, and are here. Each of these 4 is a completely different problem, and the gap between them is not a small factor. It is not 2 times harder or 10 times harder as you climb. It is more like 1,000 times harder, then 1,000,000 times harder, then 1,000,000,000 times harder. The scaling is brutal, and it is the reason so many otherwise thoughtful people underestimate the wall between us and any civilization out there. Let us begin with the first achievement, because it is the one that has genuinely, in the last decade or so, become almost easy: detecting Earth. In fact, it is easier than most people realize, and it is easier now than it was 30 years ago, and it will be far easier 30 years from now. Every second of every day, Earth broadcasts its own existence into the galaxy without asking permission, and without being able to stop. This is not a metaphor. It is a description of photons, actual particles of light, leaving our atmosphere and streaming outward at the speed of light in every direction. Some of those photons carry information about what Earth is made of. Others carry information about what lives here. And a small but growing fraction carry information that could only come from a technological civilization. Start with the simplest form. Sunlight strikes Earth. Some of it bounces back into space. Some of it is absorbed by the atmosphere. Some of it is absorbed by the oceans and the forests and the deserts and the ice caps. The light that eventually escapes, either reflected off the day side or radiated as heat from the night side, carries a chemical fingerprint of everything it touched. Astronomers on Earth have been reading this exact same kind of fingerprint from other planets for years now. It is called transmission spectroscopy for planets that pass in front of their star, and thermal emission spectroscopy for the light the planet itself glows in the infrared. When we point the James Webb Space Telescope at a planet around another star and analyze the light passing through its atmosphere, we can, right now, in this decade, detect water vapor, carbon dioxide, methane, and increasingly more complex molecules. We are still learning. Our instruments are still crude by any galactic standard, but we are doing it. The technology is real, the measurements are real, and the point is this: anything we can do with our current level of technology, a civilization even a few centuries ahead of us could do dramatically better. And a civilization tens of thousands of years ahead could do so well that Earth might as well be a lit-up billboard. What would that billboard say? It would say oxygen, in enormous quantities, roughly 21% of our atmosphere by volume. Oxygen is not a chemically stable gas to have hanging around in a planetary atmosphere by itself. It reacts, it bonds, it vanishes into rocks and oceans given enough time. If you find a planet with a persistent high concentration of atmospheric oxygen, the overwhelming inference is that something on that planet is constantly producing it. On Earth, that something is life. For roughly 2.5 billion years, cyanobacteria, algae, and later plants have been pumping oxygen into our atmosphere as a waste product of photosynthesis. Any competent astronomer within a few dozen light years of us who could resolve our atmosphere would see that oxygen signature and understand immediately what it means. But it is not just oxygen. It is oxygen plus methane. Methane and oxygen are chemically incompatible over geological timescales. They react with each other. If both are present in significant amounts at the same time, something is actively replenishing at least one of them. On Earth, that something is again biology. Methane from wetlands, from livestock, from decomposition, and now increasingly from human industry. The combined signature of oxygen and methane in the same atmosphere is one of the strongest biosignatures anyone has ever proposed, and Earth wears it like a neon sign. Beyond biosignatures, there are what astronomers call technosignatures. These are chemical or physical fingerprints that could only be produced by technology, not by biology alone. Earth has these too now. Chlorofluorocarbons, the industrial refrigerants that punched a hole in our ozone layer in the 20th century, do not occur naturally in any known planetary process. Nitrogen dioxide from industrial combustion, fine patterns of infrared heat emission from cities, the strange, artificial evenness of certain wavelengths of light on our night side, produced by sodium and mercury vapor lamps, and now increasingly by light-emitting diodes. Then there is the noise, the electromagnetic noise. For roughly 100 years, humanity has been leaking radio waves into space. Early broadcast television, early radio, radar systems built during and after the Second World War. Some of that leakage is weaker than people assume. Most of it dissipates below the background hiss of the galaxy within a few light years. But some of it, particularly military radar and deliberately transmitted messages, is bright enough to be picked up by a sufficiently sensitive receiver dozens of light years away. Now, here is what I want you to feel. All of this, every single one of these signatures, travels at the speed of light. It is free. It requires no engine. It requires no propellant. It requires no shielding. It requires no braking system. It simply leaves and it goes and it keeps going forever. A photon that left Earth's atmosphere in the year 1930 is, right now, tonight, 96 light years away from us, still traveling outward, still carrying its little piece of information about a planet with oxygen and methane and a strange new kind of radio noise beginning to bloom in its lower atmosphere. This is the first achievement, detecting Earth. And nature essentially does it for free. The second achievement, sending a signal, is only slightly harder. Once you can build a radio transmitter or a laser, you can point it at a target and light it up. Humanity has done this a handful of times already. The Arecibo message in 1974 aimed at a globular cluster, various smaller transmissions since. The energy involved is trivial by galactic standards. A civilization capable of building modest radio infrastructure can send a signal that will cross tens of thousands of light years and still be detectable at the other end. The energy required to send that signal is millions of times less than the energy required to send even a small physical object the same distance. This is one of the most important asymmetries in all of physics, and we will return to it again and again tonight, because it is the hinge on which the entire argument turns. Signals are cheap, matter is not. But here is where the neat little ladder of assumptions starts to shake. Because when most people think about advanced civilizations, they mentally skip over achievements 1 and 2 and go straight to achievements 3 and 4. They imagine ships, they imagine landings, they imagine visitors. And they do this because science fiction has trained all of us to see interstellar travel as roughly equivalent to interstellar communication. In the stories, the same civilization that sends a message can also, if it decides to, show up in person. There is rarely a strong distinction drawn between the two. In reality, the distinction is enormous, and it is enormous in a very specific direction. Sending information is easy. Sending mass is punishingly hard. Let me try to make this concrete. If you want to send a signal from Proxima Centauri, the closest star to our sun, to Earth, you need enough energy to power a radio transmitter for a short time. That is measured in kilowatts, maybe megawatts if you want a strong signal. Now, if you want to send a 1 kilogram probe from Proxima Centauri to Earth in a reasonable time, say within a century, you need enough energy to accelerate that kilogram to a substantial fraction of the speed of light, and then decelerate it again at the other end. That is measured not in megawatts, but in the total energy output of a large nuclear power plant running for days or weeks. And that is for a single kilogram, at a modest fraction of the speed of light, with no shielding, no instruments, and no crew. And that is for 1 kilogram. Scale up to a probe massive enough to carry actual instruments. A few 100 kilograms, say. And the energy requirement scales linearly with the mass. Scale up further to a crewed ship with life support, radiation shielding, fuel for deceleration, and enough consumables to keep biological travelers alive for the journey. And the energy requirement climbs into a range that is difficult to even describe in familiar units. We will get into the specific numbers in the next part. For now, I just want you to hold on to the shape of the asymmetry. Detecting a civilization is nearly free. Signaling a civilization is cheap. Sending a probe is expensive. Sending living travelers is so expensive that it might be practically impossible even for civilizations that have solved every other engineering problem we can imagine. Now let me turn the lens around and ask the question from the other direction. If we can, right now, with our current level of technology, begin to detect biosignatures on planets tens of light years away, then what could a civilization with instruments 1,000 times more sensitive detect? What could a civilization with instruments 1,000,000 times more sensitive detect? The answer, roughly, is everything. Every rocky world with an atmosphere within thousands of light years, every ocean, every ice cap, every seasonal shift in vegetation, every industrial civilization emitting infrared waste heat and strange, stable molecules. Any civilization capable of building space-based telescopes with mirrors kilometers across, which is not a violation of any known physics, just an enormous engineering project, could sit in its home system and read the surface conditions of hundreds of thousands of nearby worlds without ever leaving. They could know we are here. They could know what we are made of. They could know with reasonably high confidence that Earth hosts a technological species, and they could learn all of this without ever building a single starship. This is the split. This is the great split I want you to see clearly, because everything else in this story flows from it. The gap between knowing and going. The gap between observing and arriving. The gap between the photon that carries information for free and the atom that must be pushed, kilogram by kilogram, across an ocean of empty space that punishes anything that tries to cross it. And here is where I want you to notice something almost paradoxical. As a civilization becomes more advanced, the gap between knowing and going does not close. It widens. Because the tools for observation improve on a smooth, well-behaved curve. Bigger mirrors, better detectors, longer baseline interferometry, where multiple telescopes work together to act like one enormous telescope. Space-based observatories with mirrors made from smaller pieces assembled in orbit. Every century of progress makes it easier to sit at home and see further. But the tools for interstellar travel run into walls that do not soften with cleverness. The energy cost of accelerating mass to relativistic speeds is not an engineering problem that scales down with cleverness. It is a physical requirement rooted in the fundamental relationship between energy, mass, and velocity. You cannot invent your way past it. You can only pay it. So a civilization 10,000 years ahead of us could quite plausibly know about every technological species within a radius of several thousand light years, while still finding it prohibitively expensive to actually travel to any of them. They would be, in a very real sense, watching a galaxy full of neighbors that they cannot visit. There is a specific mental image I want to give you here, because it captures the situation better than any equation. Imagine you are standing on the shore of an enormous ocean. On the far side of the ocean, hundreds of miles away across the water, you can see faintly the lights of another city. You know the city is there. You can see its glow. On clear nights, you could even see individual lights blinking on and off. And with a good telescope, you can watch its people going about their business. Now imagine that you have no boat, and you have no aircraft. And the ocean is so deep and so wide and so violent that nothing you have ever built has been able to cross it. You can see them. You know they are real. You know they are not alone in the universe, because they are right there, and they can see you too. But neither of you can step off your shore and walk across. That is roughly the situation the galaxy might actually be in. And it is a much stranger, much lonelier situation than either we are alone or they are on their way. Before we move on to the physics of interstellar distance, I want to address one very natural objection. Someone listening right now is thinking, but we do not have any evidence yet that anyone has actually detected us. So maybe this whole framing is wrong. Maybe there is no one out there to observe us in the first place. That is a fair objection, and I want to be honest about what we actually know. We do not have confirmed detection of any extraterrestrial civilization. We have candidate signals that turned out to be natural or unexplained. We have suggestive patterns that have not been reproduced. What we have is the confirmed observation that Earth has been broadcasting its existence, biologically for billions of years, technologically for about 100, and that the galaxy contains something like 200 billion to 400 billion stars, a very large fraction of which host planets, and a meaningful fraction of those planets sit in what astronomers call the habitable zone, where liquid water is possible on the surface. We do not know how often life arises. We do not know how often life becomes complex. We do not know how often complex life becomes intelligent. And we do not know how often intelligent life builds a technological civilization. These are enormous uncertainties, and any honest treatment of the question has to acknowledge them. What tonight's story is doing is not claiming that aliens definitely exist. It is exploring a specific scenario. The scenario in which they do exist and can observe us. And asking why, in that scenario, we still might never meet them. Because that scenario, if it is true, changes everything about how we think about our place in the galaxy. It means the silence is not evidence of emptiness. It means the silence might be evidence of something much stranger. A galaxy where seeing is normal and traveling is nearly impossible. A galaxy full of watchers who cannot become visitors. And that brings us to the question that will drive the next stretch of tonight's journey. If detecting Earth is easy and signaling Earth is cheap, but sending a probe or a crew across the interstellar gulf is enormously expensive, then just how enormous is that expense? How far away, in physical terms, is the nearest star? How long would it take, using the fastest thing humanity has ever built, to actually get there? And what happens when we start to seriously grapple with the numbers, instead of hand-waving past them? Because here is the punchline of everything we have just walked through. The thing I want you to carry with you as we go deeper. Every argument about advanced civilizations that treats advanced as a single quality, as if being more advanced means being more advanced at everything, is quietly wrong. Advancement is not one skill, It is a scattered set of skills. And observation and travel are on opposite ends of that scatter. Observation gets easier and easier and easier as the civilization grows. Travel hits walls that intelligence alone cannot break through. The two skills diverge over time, not converge. The gap between what a mature civilization can see and what a mature civilization can reach is not a temporary limitation of youth. It's a permanent feature of the physical universe. The photons leaving Earth right now are 300 million meters per second worth of information about who we are. They pass Proxima Centauri in 4.25 years. They reach the nearest sun-like stars within a couple of decades, and hundreds more within a lifetime. They cross the entire galaxy in 100,000 years. That is fast. That is the fastest thing that exists. The fastest object humanity has ever launched, a spacecraft called Voyager 1, is currently moving at about 17 kilometers per second relative to our sun. At that speed, it will not reach the distance of Proxima Centauri for something like 73,000 years. And Proxima is our nearest neighbor. Move that same speed out to any of the stars that might actually host a mature technological civilization, and you are talking about journey times that stretch far beyond the recorded history of our species. That gap, the gap between the speed of light and the speed of matter, is what we are going to examine next. Because it is the first, and in some ways the simplest, of the walls that stand between a civilization that knows about Earth and a civilization that could actually come here. Distance alone might be enough to stop them. And even if distance alone is not enough, distance is only the beginning of what interstellar travel demands. So let us leave this first stretch with the image I want to plant in your mind. A galaxy where the eyes are getting sharper every century. A galaxy where the ships are stuck against a wall of physics that no amount of cleverness fully breaks. A galaxy where you can watch your neighbors across the dark and know they are watching you back, and still, both of you, remain forever unable to cross the water between your two lit shores. That is where we are going tonight. Now we start walking the distance itself, meter by meter, light year by light year, out into the emptiness that separates one star from another, so we can see with our own eyes just how wide the ocean really is. We ended just now standing on a shore, looking across a dark ocean toward the distant lights of a city we could see but not reach. That image was a metaphor. Now I want to make it concrete. I want you to feel in your bones how wide the ocean actually is, because until you have really sat with the numbers, not glanced at them, not skimmed past them, but actually let them settle into your understanding, you cannot appreciate why interstellar travel is not just difficult, but categorically different from every other kind of transportation problem humans have ever solved. Let me start close to home. When you look up at the night sky and see a star, your instinct is to think of it as far away, but manageably far away. A very long distance, yes, but the kind of distance you could imagine crossing given a fast enough vehicle and enough time. That instinct is wrong. It is not just wrong by a little. It is wrong by a factor so large that ordinary human language starts to break down when you try to describe it. Here is a small experiment. Take the fastest thing you have ever personally traveled on. For most people, that is a commercial airliner cruising at around 900 kilometers per hour. Now, imagine you could keep that airliner flying in a straight line at cruising speed, without ever stopping or refueling. How long would it take to reach the nearest star system, Proxima Centauri, which sits 4.24 light years away? The answer is roughly 5 million years. Not 5,000. Not 500,000. 5 million years. That is longer than the entire evolutionary history of the genus Homo, from its earliest ancestors to modern humans. If a group of early hominids had boarded a Boeing 747 around the time our earliest tool-using ancestors walked the African savanna and started flying in the direction of the nearest neighboring star, they would still be in transit today, and they would still have a very long way to go. That is the ocean we are talking about. Now, obviously, we are not going to send starships at the speed of commercial jets. We can do much better than that. And we already have. The fastest object humanity has ever built and released into space is a small spacecraft called Voyager 1, launched in 1977. Voyager 1 is currently more than 24 billion kilometers from Earth, moving outward at about 17 kilometers per second relative to our Sun. That is roughly 61,000 kilometers per hour, or about 68 times faster than the airliner in our earlier thought experiment. At that speed, at humanity's actual best, using our fastest existing hardware, how long would it take Voyager 1 to reach Proxima Centauri if it were pointed in that direction, which it is not? Roughly 73,000 years. Sit with that number for a moment. 73,000 years. That is longer than recorded human history multiplied by 10. That is longer than the time between the last ice age and today, multiple times over. That is comparable to the entire span during which anatomically modern humans have painted on cave walls, buried their dead with grave goods, and told each other stories about the stars. And that is just to reach our nearest neighbor. Move further out, say, to the star system called TRAPPIST-1, which hosts several potentially habitable planets and sits about 39 light years away, and Voyager's travel time balloons to over 600,000 years. Move out to something like Kepler 452b, one of the more Earth-like exoplanets we have found, sitting about 1,400 light years away, and you are talking about a transit time approaching 25 million years. 25 million years. That is roughly the amount of time that has passed since the last common ancestor of humans and modern monkeys walked the Earth. Now here is where I want you to pause and hold two very different numbers in your head at the same time, because the contrast is the whole point of what we are doing here. A photon, a single particle of light, leaving Earth today, reaches Proxima Centauri in 4.25 years. A photon from Earth reaches TRAPPIST-1 in 39 years. A photon from Earth reaches Kepler 452b in 1,400 years. Those are long times by human standards, but they are unimaginably shorter than the transit times for physical objects at Voyager's speed. The ratio between the speed of light and the speed of our fastest hardware is roughly 17,000 to 1. 17,000. This is the asymmetry I mentioned earlier, and now you can see it in raw numbers. Signals move at the maximum speed the universe allows. Matter, when we push it with the best engines we have ever built, moves at roughly 1/17,000th of that speed, which means if we are going to send a physical object across the interstellar gulf in anything remotely resembling a useful amount of time, we have to do something dramatically better than Voyager. Not a little better. Not twice as fast. Not 10 times as fast. Something like 1,000 times faster, or 10,000 times faster, or more. And this is where the physics starts to bite. Let me introduce you to a concept that shapes everything that follows in this story. It is called the tyranny of the rocket equation. And it is one of the reasons interstellar travel is not simply harder than travel between planets, but is a fundamentally different category of engineering problem. Every rocket that has ever flown works on the same basic principle. You carry fuel with you. You burn that fuel and throw the exhaust out the back at high speed. The reaction pushes you forward. The trouble is, the fuel itself has mass, and you have to accelerate all of it along with your spacecraft until you burn it, which means the more fuel you carry, the more fuel you need to carry, because you need extra fuel to push the fuel. This becomes an exponential problem very quickly. To double your final velocity, you do not need twice as much fuel. You need something more like 10 times as much fuel, or 100 times as much, depending on the specifics of your engine. For travel within our solar system, the rocket equation is punishing but survivable. The Saturn V that took us to the moon was mostly fueled by mass. To leave the solar system entirely, the way Voyager did, you have to use gravitational slingshots off the giant planets, because carrying enough chemical fuel to reach escape velocity directly would be prohibitive. Now try to apply the rocket equation to interstellar distances. To reach Proxima Centauri in, let us say, 100 years, a long time, but at least within the reach of a multi-generational human institution, you need to travel at roughly 4% of the speed of light. That is about 12,000 kilometers per second, which is over 700 times faster than Voyager. Using chemical rockets, the amount of fuel required to accelerate even a small probe to that velocity is greater than the mass of the observable universe. That is not a joke. That is what the math says. Chemical propulsion is not just insufficient for interstellar travel, it is so insufficient that the numbers stop making physical sense. Okay, chemical rockets are out. What about something more advanced? What about nuclear propulsion? There are several proposed nuclear approaches, and they are meaningfully better than chemical rockets. A nuclear thermal rocket, which uses a nuclear reactor to heat propellant and throw it out the back, could potentially achieve exhaust velocities roughly double those of chemical engines. A nuclear electric drive, which uses a reactor to power ion engines that accelerate charged particles to very high speeds, could achieve even better efficiency, though with much lower thrust. In the 1950s and 60s, there was a serious design study called Project Orion that proposed detonating small nuclear bombs behind a large plate on the back of a spacecraft, essentially riding the shockwaves outward. Orion could, in principle, have reached a few percent of the speed of light with the technology available at the time, though it was never built and would have raised enormous political and environmental problems if it had been. Nuclear approaches close some of the gap. They do not close all of it. Even the most optimistic nuclear designs top out somewhere in the range of 10% of the speed of light, and reaching that speed with a useful payload requires enormous vehicles carrying enormous amounts of nuclear material. And here we run into a problem that we will develop further in a moment, but which I need to introduce now. Reaching a high velocity is only half the problem. You also have to stop when you arrive. Every joule of energy you spend accelerating has to be matched by a joule of energy spent decelerating, because a spacecraft moving at 10% of the speed of light does not stop by itself. It flashes through the target star system in a matter of hours, and then continues into the dark on the far side, forever. We will come back to that. For now, hold on to the fact that even our most ambitious nuclear propulsion concepts, which represent enormous leaps beyond current chemical technology, still only get us to roughly 1/10 the speed of light, and only if we solve the deceleration problem, which we mostly have not. Before we move on, I want to be more specific about a few of the propulsion concepts I mentioned in passing, because the popular imagination has invested a lot of hope in them, and it is worth understanding where each one actually stands. Fusion propulsion is probably the most frequently invoked. The idea is straightforward: use the same physics that powers our sun, confining hydrogen isotopes at extreme temperatures and pressures until they fuse into helium and release energy. In principle, a fusion rocket could achieve exhaust velocities of several percent of the speed of light, which is far better than any chemical or fission approach. There is a well-studied design from the 1970s called Project Daedalus, developed by the British Interplanetary Society, which sketched a fusion-powered probe that could reach Barnard's star in about 50 years. The design is thoughtful. The physics is not obviously wrong. There is one small problem. Humanity has not yet built a fusion reactor that produces net energy for any sustained period. We are decades into the effort, and while progress is real, controlled fusion at the scale required for a starship remains an unsolved engineering problem. An advanced civilization might well have solved it. But the design gets you to Barnard's star in 50 years only if you are content with a flyby. Deceleration is not part of the plan. Antimatter propulsion is the theoretical champion of efficiency. When matter and antimatter meet, they annihilate completely, converting essentially all of their mass into energy. No chemical or nuclear reaction comes close to this efficiency. In principle, a spacecraft powered by matter-antimatter annihilation could achieve any velocity short of the speed of light, limited only by how much antimatter you can carry and how well you can direct the resulting energy. The problem is producing antimatter in the first place. Every antimatter particle we have ever made has been produced in high-energy particle accelerators, one atom at a time, at extraordinary energy cost. To power even a small starship, you would need to produce and store an amount of antimatter that would take our current civilization longer than the age of the universe to manufacture. An advanced civilization might have more efficient production methods, but the fundamental problem, that producing antimatter requires at least as much energy as it releases when annihilated, is not going away. The Bussard ramjet deserves a special mention because it is one of the most beautiful failed ideas in the history of interstellar propulsion. Proposed in the 1960s by physicist Robert Bussard, it suggested that a spacecraft could scoop up interstellar hydrogen atoms with an enormous magnetic funnel, fuse them for energy, and thereby travel indefinitely without carrying its own fuel. For decades, the ramjet was a staple of hard science fiction. Then, in subsequent analyses, physicists began to realize that the drag from the scooping process actually exceeds the thrust from the fusion process at almost every plausible operating regime. The ramjet, in other words, breaks itself faster than it can accelerate. It looks like a solution and turns out to be an anchor. I mention these three not to catalogue every idea, but to make a specific point. Every propulsion concept that could plausibly get a spacecraft across the interstellar gulf in a reasonable time either does not yet exist as working technology, or runs into fundamental problems that no amount of engineering cleverness has yet resolved. There is nothing here that a mature civilization could not eventually push forward. But the pattern is clear. Each concept trades one set of impossible costs for another. Now, someone listening right now is going to be thinking, but we're just at the beginning of our technological development. A civilization thousands or millions of years ahead of us would surely have propulsion technologies we cannot even imagine. Why assume that our limitations are their limitations? That is a legitimate and important objection, and I want to take it seriously. Because the honest answer is more nuanced than either no, physics is physics, or yes, anything is possible with enough time. Here is the truth. There are propulsion concepts that are more advanced than anything humanity has built, but which do not require inventing new physics. Beamed propulsion, where a giant laser or microwave array in one star system pushes a lightweight sail toward a target, is one of the more promising ideas, and we will discuss it in more depth shortly because it is the core of a real modern proposal called breakthrough starshot. Antimatter propulsion, where matter and antimatter annihilate to release energy at the theoretical maximum efficiency, is another. Fusion propulsion, if we can ever make it work, would sit somewhere between fission and antimatter in terms of energy density. None of these violate known physics. All of them face enormous engineering challenges that scale with the size of the payload. And all of them still bump into the same fundamental problem. Pushing mass to a high fraction of the speed of light requires energies that are not just large, but astronomically large, and the energy requirement is set by the laws of physics themselves, not by our current level of engineering sophistication. This is the point I want you to really absorb, because it is where a lot of casual thinking about interstellar travel goes wrong. There is a tendency to imagine that any physical limit we currently face is just a temporary limitation of our technology, and that a sufficiently advanced civilization would have found workarounds. And for many kinds of engineering problems, that is exactly right. A civilization 1,000 years ahead of us will have computers we cannot imagine, medical treatments we cannot imagine, materials science we cannot imagine. But some limits are not engineering limits. Some limits are structural features of the universe itself. The speed of light is 1. The energy required to accelerate mass to a given velocity is another. The relationship between kinetic energy and velocity, the fact that doubling your speed quadruples your energy cost, and going from 90% to 99% of the speed of light multiplies your energy cost by a factor of many, is not an engineering limitation. It is a description of how the universe works. Advanced civilizations do not get to opt out of this. They may find much more efficient engines. They may find much better ways to store and release energy. But the fundamental relationship between energy, mass, and velocity is a wall that intelligence alone cannot break through. Because intelligence is a property of minds, and the wall is a property of physics. Let me put this differently. Imagine we're discussing how a sufficiently advanced civilization might solve some engineering problem. If the problem is build a computer 1,000,000,000,000 times more powerful than current ones, the answer is almost certainly wait and figure it out. There is no wall in physics that says computing cannot keep improving. If the problem is cure aging, the answer is probably similar. If the problem is generate more energy than we currently do, again, the answer is probably yes, given enough time. But if the problem is how do we accelerate a spacecraft to a high fraction of the speed of light without paying the energy cost that physics says we have to pay, the answer is different. Because the energy cost is not a symptom of underdeveloped technology. The energy cost is the physics. It is what accelerating a spacecraft to a high fraction of the speed of light means. You cannot subtract it out any more than you can subtract out the fact that 2 + 2 = 4. It is not a bug to be worked around. It is the basic accounting of the universe. There is one wrinkle in the relativistic story that I want to bring in here, because it is genuinely strange, and it is the one place where the physics offers something that almost looks like a gift. Until you look at it closely and see that the gift comes with a very sharp edge. When a spacecraft moves at a substantial fraction of the speed of light, time on the spacecraft does not pass at the same rate as time back home. This is not science fiction. It is one of the most thoroughly confirmed predictions of relativity, tested countless times with atomic clocks on aircraft and satellites. Time actually slows down for the traveler, as measured by anyone who stayed behind. The faster you go, the more pronounced the effect becomes. At 99% of the speed of light, 1 year on the ship corresponds to about 7 years back home. At 99.9%, one shipboard year corresponds to about 22 home years. At 99.99%, one shipboard year corresponds to over 70 home years. For a crew, this sounds like a solution to the whole problem. If you can move fast enough, the journey becomes short from your perspective, even if it takes centuries from the perspective of the civilization that sent you. A trip to a star 50 light years away at 99.9% of the speed of light would feel like about 2 years to the crew on board. A manageable duration, well within a human lifetime. But look at what that requires. To move at 99.9% of the speed of light, you have to pay the full Lorentz factor energy cost, which, as we just discussed, climbs toward absurd values. You have to survive a dust bullet environment far worse than anything we will describe in a few minutes, and you have to solve the braking problem at those speeds, which is dramatically harder than at slower speeds, because you need to shed enormous amounts of kinetic energy in a short shipboard time. There is also a stranger cost that people rarely notice. Time dilation is a one-way relationship with your home civilization. While you experience 2 years, your home world experiences over 1,000. When you arrive at your destination, and if you turn around and come back, the civilization that launched you is not the civilization you return to. Institutions have collapsed. Languages have shifted. The people who funded your mission have been dead for 40 generations. The scientific questions you were sent to answer may have been solved by other means, or may no longer matter. The results you carry may be irrelevant by the time you deliver them. For a physical mission that wants to actually contribute knowledge back to its launching civilization, time dilation is not a gift. It is a form of exile. The crew survives the journey, but the civilization that sent them does not survive the wait. Any advanced society considering such a mission has to reckon not just with whether the crew can make the trip, but with whether the civilization can hold itself together long enough to still care when the trip is over. Which means that even the one relativistic effect that seems to help the traveler ultimately deepens the isolation between civilizations rather than closing it. Time dilation shrinks the journey for the ship, but it does nothing to shrink it for the sender. The gap between departure and return remains centuries long from anyone's perspective, except the traveler's. And a traveler who returns to a civilization that has forgotten them is a strange kind of success. So when we say that interstellar travel is hard, we do not just mean it is hard for us. We mean it is hard in a way that scales with the fundamental structure of reality. A civilization 10,000 times more advanced than us can build a ship 10,000 times more sophisticated than anything we can imagine. And that ship still has to pay the energy cost of moving mass across distance. The cost does not go away because the ship's builders are clever. It goes away only if the ship is very light, or moves very slowly, or does not have to stop when it arrives. Now, I want to introduce a distinction that will become crucial in the parts to come, because it explains why some people are more optimistic about interstellar travel than others. The distinction is between two very different kinds of missions. The first kind is a flyby mission. In a flyby, you accelerate your spacecraft to a high velocity, aim it at a target star system, and then let it coast. When it arrives at the target, it flashes through the system at whatever velocity it was moving, taking measurements as fast as it can, and then continues out the other side into deep space. It never stops. It never orbits. It never lands. The most famous example in our own history is Voyager 2, which performed flybys of Jupiter, Saturn, Uranus, and Neptune, grabbing hours or days of data at each planet before continuing outward. The second kind is a rendezvous mission. In a rendezvous, you accelerate to a high velocity, and then, when you approach the target, you decelerate to match the target's motion. This lets you enter orbit, spend extended time in the system, and potentially even land on a planet. Every mission that has ever orbited another planet in our solar system has been a rendezvous mission. The energy cost of a rendezvous is roughly double the energy cost of a flyby, because you have to spend as much energy stopping as you spent starting. For interstellar travel, the difference between flyby and rendezvous is enormous, because at the speeds involved, a flyby gives you only a very brief window to gather data. A spacecraft moving at 1/10 the speed of light through a solar system the size of ours would cross from one edge to the other in a matter of hours. That is enough time to snap some photographs, but nowhere near enough time to conduct extended observations, follow up on interesting findings, or communicate meaningfully with anything on the surface of a planet. So the flyby mission is dramatically easier, and delivers dramatically less. The rendezvous mission is dramatically harder, and delivers a real scientific presence. And any civilization that wants to actually visit Earth, in the meaningful sense of the word, arriving, staying, observing, interacting, needs a rendezvous, not a flyby. Which means, on top of everything else we have described, absorbing the full arrival penalty on top of the departure cost. Let me put one more number on the table before we move on, because I think it makes the situation vivid. Suppose an advanced civilization somewhere within, say, 50 light years of us decides to send a rendezvous mission to Earth. Suppose they have propulsion technology far beyond ours. Let us say they can push a probe to 20% of the speed of light, which sits at the very edge of what our most ambitious modern proposals even attempt, and only for probes weighing a few grams rather than anything with real scientific mass. Even with this generous assumption, the round-trip time for a mission that arrives at Earth, spends some time observing, and then reports back to its home world is at least 300 years. 250 years to get here, plus 50 years for the light of the report to travel back, plus however long the mission spends on site. If they want the results within a single institutional lifetime, they have to be extraordinarily patient and extraordinarily long-lived as an organization. And that is for a target only 50 light years away. For targets 100 or 200 light years away, where a very large fraction of interesting nearby stars actually sit. The round-trip time balloons past 600 years, past 1,000 years, past 1,200 years. These are timescales longer than any human institution has ever survived. Cathedrals fall in less time than that. Empires rise and vanish in less time than that. Languages evolve into unrecognizability in less time than that. Any civilization contemplating an interstellar mission has to ask itself whether the institution funding the mission will still exist when the mission returns its results. And that is a question with no obvious answer, even for a civilization vastly more stable and long-lived than ours. So here is where the distance question leaves us. Distance alone, without any other complication, is already enough to make interstellar travel a completely different category of undertaking from anything humans have ever done. The nearest star is farther than 5 million years of airliner flight. Our fastest existing spacecraft would take over 70,000 years to reach it. Even our most ambitious proposed propulsion systems bring that number down to something like a century for a small flyby probe, and much longer for anything with real scientific instrumentation, real payload mass, or the ability to actually stop when it arrives. And the timescales for two-way missions, go there, look around, come back to report, stretch beyond the lifespan of any institution we have ever built. An advanced civilization looking at these numbers is not looking at a difficult project. They are looking at a project on a scale that requires either radical patience, radical propulsion, or radical decisions about what is actually worth doing. And we have not even started talking about the harder problems yet, because distance, as it turns out, is only the beginning. Now we are going to look at what happens when you actually try to move that fast. The energy requirements that grow toward infinity. The single grain of dust that hits your ship with the force of a hand grenade. The cosmic radiation that shreds electronics and biology alike. The braking problem that turns every fast journey into a two-way energy budget. And the strange, brutal reality that going faster does not solve the interstellar problem. Going faster creates entirely new problems that going slower did not have to face. The ocean, it turns out, is not just wide. It is full of teeth. And the faster you try to cross it, the sharper those teeth become. Let us go see them. We left off with the raw shape of the problem. The nearest star is unimaginably far. Our fastest existing spacecraft would take over 70,000 years to reach it. Even our most ambitious propulsion concepts stretch the journey into centuries. And any two-way mission, go there, look, come back to report, takes longer than any human institution has ever survived. But there is an obvious response to all of this. And it is the response I want to carefully take apart now. The response goes like this. Fine. At slow speeds, the journey takes centuries. But what if we just go faster? What if we push our ships to a substantial fraction of the speed of light? Then the journey compresses. Then Proxima becomes a few decades away instead of centuries. Then TRAPPIST-1 becomes a lifetime instead of 10,000 lifetimes. Surely a sufficiently advanced civilization would just build faster ships and be done with the problem. It is a reasonable instinct. It is also, unfortunately, wrong in a very specific and very interesting way. Because when you actually try to build a spacecraft that moves at a substantial fraction of the speed of light, the physics does not simply get harder. The physics gets qualitatively different. New problems appear that did not exist at slower speeds. Old problems get so much worse that they change from engineering challenges into fundamental limits. And the very act of trying to shrink the ocean by moving faster fills the ocean with new kinds of danger that a slower ship would have never encountered. Let me walk you through this in 3 stages. First, the energy wall. Why going fast is not just expensive, but climbs toward physically absurd costs the closer you get to the speed of light. Second, the dust bullets. Why interstellar space, which looks empty, is not empty enough to survive at relativistic speeds. And third, the braking problem. Why arriving is a separate physics problem from departing, and why forgetting about it turns every fast mission into a very expensive flyby that flashes past its target and disappears into the dark forever. Start with the energy wall. In everyday life, when you double your speed, you roughly quadruple the energy you need. This is a familiar relationship. A car going 100 kilometers per hour needs about 4 times the kinetic energy of a car going 50. This is why highway crashes are so much more destructive than city crashes. The energy scales with velocity squared. That is the basic Newtonian formula, and it works fine as long as you are moving at speeds much slower than light. But something strange happens as you approach the speed of light. The Newtonian formula breaks down and is replaced by a relativistic version. And the relativistic version is much crueler. Instead of energy scaling with velocity squared, it scales with a factor called the Lorentz factor, which stays close to 1 at low speeds, but climbs toward infinity as you approach the speed of light. At 10% of the speed of light, the Lorentz factor is only about 1.005, meaning you pay roughly the Newtonian cost, with a small relativistic surcharge. At 50%, the Lorentz factor is about 1.15, still manageable. At 90%, it climbs to about 2.3. At 99%, it is about 7. At 99.9%, it is about 22. At 99.99%, over 70. What this means in practical terms is that if you want to build a spacecraft that goes 99% of the speed of light, you do not just pay a lot of energy. You pay so much energy that the numbers stop resembling anything anyone would consider building. Even for a small probe weighing a few hundred kilograms, the kinetic energy required to reach that velocity is comparable to the total electrical output of human civilization over years or decades. For a spacecraft massive enough to carry meaningful instruments, life support, or crew, the energy requirement climbs into ranges that do not correspond to any energy source we know how to build. And here is the important point. That energy requirement is not an engineering problem. It is not a limit of our current technology. It is what moving at 99% of the speed of light means. In the same way that climbing a 10,000 meter mountain means gaining 10,000 meters of altitude. You cannot get to the top of the mountain without gaining the altitude. You cannot move a spacecraft at 99% of the speed of light without paying the energy cost. A civilization 10,000 years ahead of us might have far better energy sources than we do. They might have fusion reactors, or matter-antimatter reactors, or something we cannot imagine. But whatever their energy source, they still have to feed that energy into their spacecraft, and the amount of energy they have to feed in scales with the Lorentz factor, which climbs toward infinity as the speed climbs toward the speed of light. There is no way around this. It is not a problem you outgrow. It is a wall built into the structure of physics. In practice, no serious modern proposal tries to reach 99% of the speed of light. The energy requirement is too extreme. The most ambitious real proposal on the books today is Breakthrough Starshot, announced in 2016 with funding from private investors and technical advice from some of the most respected physicists alive. Starshot aims to send a small fleet of tiny probes, each one about the size and mass of a postage stamp, with a small light sail attached, to the Alpha Centauri system, arriving in about 20 years by traveling at roughly 20% of the speed of light. 20% is a lot. It is more than any spacecraft humanity has ever moved. But it is also chosen deliberately to avoid the worst of the energy wall. At 20% of the speed of light, the Lorentz factor is only about 1.02, meaning the energy cost is essentially the Newtonian cost with almost no relativistic penalty. Starshot works by keeping the payload absurdly small, a few grams, and firing a massive ground-based laser array at the light sail to push it. The laser array is proposed to be a large ground-based installation, potentially covering a square kilometer or more of Earth's surface, and it needs to deliver something like 100 gigawatts of power in a coherent beam. That is roughly the average electrical output of an industrialized nation, focused into a laser aimed at a probe the size of a business card. Starshot is real. It is being seriously studied. And even Starshot, with all of its ingenuity, has severe limitations. The probes it would send are so small that they cannot carry any real scientific instrumentation. They cannot decelerate. They cannot orbit. They cannot rendezvous. They will flash through the Alpha Centauri system in a few hours, hopefully snapping a few photographs and relaying them back to Earth over a communication link that will take 4 years to arrive. And Starshot only works because Alpha Centauri is our closest neighbor. Scale it up to a target 10 times further away, and the laser array needs to be 100 times more powerful, or the acceleration phase needs to last much longer, and the whole project starts to buckle under its own requirements. So even the most ambitious real proposal we have is fundamentally a flyby with tiny probes, and it exists at the edge of what physics permits without paying the full Lorentz factor cost. Anything faster, anything larger, anything with actual scientific capabilities starts to run headlong into the energy wall. Okay, suppose we accept the energy cost. Suppose the advanced civilization we are imagining has decided to pay it. They are willing to devote the output of a small star to accelerating a spacecraft toward Earth. Are they home free once the ship reaches cruising speed? No. They are not even close. Because interstellar space, which looks empty from the surface of the Earth, is not empty in the way you need it to be when you are traveling at a substantial fraction of the speed of light. This is the dust bullet problem, and it is one of the most underappreciated challenges in interstellar travel. So I want to spend some real time on it. The space between stars is not a perfect vacuum. It is filled with a thin scattering of hydrogen atoms, helium atoms, and very small particles of solid material. Dust grains ranging from a few nanometers to a few micrometers across, along with occasional larger particles. In the neighborhood of our solar system, the density of this interstellar medium is roughly 1 atom per cubic centimeter, plus a much smaller number of dust grains. By any standard of everyday experience, that is an extraordinarily good vacuum. It is emptier than the best vacuum chambers we can build in laboratories on Earth. If you were standing in interstellar space, you would not notice the medium at all. But you are not standing in interstellar space. You are traveling through it at a substantial fraction of the speed of light. And at those speeds, the arithmetic of collision changes completely. When a stationary hydrogen atom sits in space, it is harmless. It has essentially no kinetic energy relative to anything nearby. But when your spacecraft slams into that same hydrogen atom at, say, 10% of the speed of light, the atom becomes a projectile with an enormous amount of kinetic energy relative to your ship. The atom itself has not changed. Your ship has. From your ship's frame of reference, that stationary hydrogen atom is now a bullet traveling at 10% of the speed of light, straight at your hull. A single hydrogen atom at that speed is not catastrophic. It carries only a tiny amount of energy. But you are not encountering a single atom. You are encountering a stream of them, continuously, for the entire duration of your journey. Over a distance of light years, at a density of 1 atom per cubic centimeter, you sweep up an enormous number of these atoms, and each one deposits its energy into your ship's forward-facing surfaces. The result is essentially a form of radiation. Your ship's front becomes bombarded by a stream of high-energy particles that behaves, physically, like a very intense particle accelerator beam aimed directly at your hull. Materials exposed to this beam degrade, they erode, they heat up. They accumulate radiation damage that changes their chemical and structural properties. Electronics behind the shielding get bombarded by secondary particles. Biological tissue, if there is any on board, gets shredded at the molecular level. There is another layer to the particle problem that deserves its own mention, because it is different from the dust bullets we are about to discuss. The interstellar medium is threaded through with magnetic fields, weak by planetary standards, but present everywhere. And it contains a background flux of charged particles arriving from all directions. Most of them the products of ancient supernova explosions and active galactic events. These charged particles are what we call cosmic rays, and even at rest, they carry enough energy to damage electronics and biology. When your ship is stationary, the cosmic ray flux is a background hazard that can be managed with modest shielding. When your ship is moving at 10% of the speed of light, the cosmic ray flux from the direction you are traveling becomes dramatically more energetic, because you are essentially running into those particles at combined velocities that push their effective energies significantly higher than they would be against a stationary target. And unlike neutral hydrogen atoms and dust grains, charged particles interact with your ship in complex ways. They spiral around any magnetic fields your ship carries. They generate secondary radiation when they strike shielding, producing showers of new particles that can be more dangerous than the originals. They accumulate inside electronic circuits, gradually degrading semiconductor materials in ways that are difficult to repair. An advanced civilization might use its own magnetic field, generated by superconducting coils on the ship, to deflect incoming charged particles before they reach the hull. This is one of the more promising shielding ideas for long-duration missions. But generating a magnetic field strong enough to meaningfully deflect relativistic cosmic rays requires enormous power, adds mass, and creates its own complications. The ship becomes a target for any charged material in the surrounding medium, and the field can interact unpredictably with the interstellar magnetic environment. It is a real proposal, and it might help. It does not eliminate the problem. For hydrogen atoms alone, the problem is severe but potentially manageable with thick enough shielding. But hydrogen atoms are not the only thing in interstellar space. There are also dust grains, and dust grains are much, much worse. A dust grain the size of a small speck, say 10 micrometers across, still invisible to the naked eye and massing about a millionth of a gram, striking a spacecraft at 10% of the speed of light carries kinetic energy comparable to a small explosive charge. Larger grains, and there are larger grains, hit much harder. That is not an exaggeration. That is what the numbers say. A single microscopic speck of interstellar dust moving at relativistic speeds relative to your ship delivers an explosive impact. And you're not hitting one dust grain, you are hitting many of them over the course of the journey. The exact number depends on the density of dust along your path and the length of the journey. But for a trip to Proxima Centauri at 10% of the speed of light, a spacecraft with a modest cross-section would encounter enormous numbers of dust grains along the way. Most would be small enough to cause only surface erosion. But over the course of the journey, enough larger grains would be encountered that catastrophic impacts become a serious statistical concern rather than a freak accident. There is no known material that shrugs off this kind of bombardment indefinitely. Any leading surface of the spacecraft will erode. Any shielding will accumulate damage. Any electronics behind the shielding are vulnerable to secondary particle showers. And unlike the energy war, which you can, at least in principle, pay your way past with more fuel, the dust bullet problem is a matter of what your spacecraft is made of and how much of it you are willing to grind away over the course of the journey. Various shielding strategies have been proposed. You could put a thick shield of ablative material at the front of the spacecraft, designed to slowly erode and absorb impacts while protecting the rest of the ship. You could use magnetic fields to deflect charged particles, though this doesn't help with the neutral dust grains. You could split the ship into a leading shield and a trailing payload, connected by a long cable. You could even try to sweep the path in front of the ship with lasers or particle beams that pre-vaporize incoming dust. All of these ideas exist in the literature. None of them fully solves the problem, and all of them add mass, complexity, and energy cost to a mission that is already at the ragged edge of feasibility. And the faster you go, the worse the dust bullet problem becomes. At 10% of the speed of light, dust grains hit like grenades. At 50%, they hit like artillery shells. At 90%, they hit like small tactical weapons. Going faster does not shorten the journey enough to compensate for the exponentially worsening impact energies. There is a middle range, probably somewhere between 5 and 20% of the speed of light for realistic missions, where the trade-off between journey time and dust damage is least bad. Above that range, the damage curves start to win. So even for an advanced civilization willing to pay the energy cost, there is a hard practical ceiling on how fast their ships can safely go through interstellar space. It is not the speed of light. It is far below the speed of light. And that ceiling is set not by their engines, but by the physical hostility of the medium they're trying to cross. Now, let me add the third layer to this problem, because it is the one that most surprises people when they first hear it. Even if you pay the energy cost, and even if you survive the dust bullets, you still have to solve the arrival problem. And the arrival problem is essentially the entire journey a second time, in reverse. This is the braking problem, and it deserves careful attention because it is the most commonly forgotten piece of the interstellar puzzle. Every joule of energy you spend accelerating your spacecraft is 1 joule of kinetic energy that the spacecraft carries at cruising speed. When you arrive at your target, all of that kinetic energy is still there. It does not go away. If you want to actually stop at the target, to enter orbit, to conduct extended observations, to interact with anything in the system in any meaningful way, you have to remove all of that kinetic energy. And removing kinetic energy costs the same amount of energy that adding it did. This means an interstellar mission that arrives at its destination and stops requires roughly twice the energy of an interstellar mission that just flies through. And it requires that half of the energy be deliverable at the far end of the journey, not at the launching civilization's home system, which raises an immediate and severe problem. How do you deliver that energy? For chemical or nuclear rockets, the standard approach is to carry the fuel with you. You spend the first half of the journey accelerating using fuel you brought. You spend the second half decelerating using more fuel you brought. But the rocket equation, as we discussed earlier, means that carrying twice as much fuel is far worse than doubling your energy cost. It typically means multiplying it by 10 or more, because you have to accelerate all the extra deceleration fuel along with the ship. For interstellar velocities, the amount of fuel required to both accelerate and decelerate a meaningful payload becomes prohibitive even with the most exotic propulsion concepts. For beamed propulsion, the Starshot approach, the problem is even more stark. The laser array that pushes the sail on the way out is anchored in the launching solar system. There is no equivalent laser array at the destination to push the sail back into stability at the far end. So Starshot's baseline mission is explicitly a flyby. There is no plan to stop. The probes flash through Alpha Centauri and continue into the dark. Some proposals try to solve this in creative ways. One idea is to use a magnetic sail, which deploys after the ship arrives at the destination and uses the destination system's stellar wind to slow the ship down over a long period. Another idea is for the arriving civilization to have already built a receiver laser at the target system, which is obviously not possible if you have not been to the target yet. A third idea is to send along a second, smaller sail that separates near the destination and reflects laser light backward at the main sail to decelerate it. But the math on this is very tight, and it requires precisely the right geometry and precisely the right kind of laser physics to work at all. None of these solutions is a decisive win. All of them add complexity and reduce the useful payload. And the fundamental problem remains: the second half of the journey, the arrival half, is at least as hard as the first half, and often harder, because you cannot use the same infrastructure to solve it. This is why so many serious analyses of interstellar travel conclude that flybys are dramatically easier than rendezvous missions, and that any mission which actually wants to stop at its destination, to enter orbit, to explore, to interact, pays approximately double the energy cost of a mission that just flashes through. And this brings us back to the central question of tonight's story. If an advanced civilization wanted to actually visit Earth in the meaningful sense, arriving, staying, observing, interacting, they need a rendezvous, not a flyby. They need to solve the braking problem. And solving the braking problem, on top of paying the energy cost of the acceleration phase, and on top of surviving the dust bullets during the cruise phase, adds up to a mission profile that is not just difficult, but is starting to look, from a pure engineering standpoint, like something that a mature civilization might rationally decide is not worth doing. Let me put this in the most vivid way I can. Imagine a civilization somewhere within, say, 100 light years of us. They have detected Earth. They know we exist. They have read our atmospheric spectrum. They have caught the drifting edges of our radio noise. They know, with high confidence, that there is a technological species on the third planet from the Sun of this small yellow star, and they are considering whether to send a physical mission. They calculate the requirements. To arrive within a reasonable fraction of an institutional lifetime, let us say 200 years, they need to travel at roughly half the speed of light. That means paying the Lorentz factor energy cost for a half-light speed cruise, which is enormous but perhaps not absurd for a civilization that harvests significant fractions of its star's energy output. It means surviving hundreds of thousands of dust grain impacts over the course of the journey, each carrying explosive energies, requiring enormous shielding. It means decelerating from half the speed of light at the destination, doubling the energy budget, and requiring some scheme to deliver the deceleration energy that does not rely on infrastructure they have not yet built at the target. And after all of that, they get a probe or a ship at Earth, which then has to send its data back over another 100 years of light travel time. Now, compare this to the alternative. Build a bigger telescope in their home system, spend a tiny fraction of the energy, and read Earth's atmosphere continuously from the comfort of home, with data arriving as fast as light itself can carry it. The bigger telescope option delivers essentially all of the scientific information that a flyby probe would deliver at a small fraction of the cost, with results available immediately rather than after a 2-century wait, and without any of the engineering risk. The bigger telescope is the rational choice. It is the choice a mature civilization would probably make. Not because they are lazy, not because they are uncurious, but because the ratio of information gained to energy spent for observation versus travel is not close. It is not 2-to-1 or 10-to-1. It is more like 1,000,000-to-1 or 1,000,000,000-to-1 in favor of staying home and looking. And this is the shape of the interstellar problem that drives us to the final piece. The energy wall makes fast travel prohibitively expensive. The dust bullets make fast travel dangerous. The braking problem doubles the whole budget. And after paying all of these costs, you get a physical presence at your target, which is scientifically valuable, but not overwhelmingly more valuable than what you could learn by observation alone. For a machine, this trade-off might still be worth making some of the time. A probe does not eat. A probe does not age. A probe does not get bored. A probe can survive centuries of transit with only slow degradation, especially if it is designed for self-repair. There are versions of this mission profile that make sense for autonomous machines, and we will explore them shortly. But for a living traveler, for a biological crew, or a mind embedded in fragile hardware, the calculation gets much worse. Because everything we have discussed tonight so far has been about the ship. Now we are going to talk about the passenger, and what the passenger has to survive on a journey like this may be the final wall that separates observation from arrival. The physics of interstellar travel is unforgiving. The biology of interstellar travel may be impossible. Let us go see why. We've spent this whole conversation building a case. We began by separating the assumption that advanced civilization means eventual arrival into 4 distinct achievements: detecting, signaling, sending a probe, and sending a living traveler. And we saw that each rung of that ladder is dramatically harder than the last. Then we walked the ocean of interstellar distance and saw that even our fastest existing spacecraft would take over 70,000 years to reach our nearest neighbor. Then we watched the physics turn hostile when we tried to shrink that ocean by moving faster. The energy wall climbing toward absurdity, the dust bullets ripping through holes at relativistic speeds, and the braking problem forcing every fast mission to pay its energy cost twice over. But we have been talking about ships, about hulls, engines, shielding, propellant, sails. Machines can be built. Machines can be engineered to survive things that would kill anything alive. And there is a very natural response at this point in the story to say, fine, biological travel is hard, but what about a probe? What about a machine? What about the kinds of self-repairing, self-replicating autonomous systems that physicists have been sketching for decades? Surely, if living travelers cannot cross the Gulf, machines can. This is a serious argument, and I want to take it seriously in these final stretches. Because it turns out that even for machines, the story is more complicated than it first appears. And once we have grappled with what interstellar travel really costs for both flesh and metal, we can arrive at the strange, quiet conclusion that this whole story has been walking toward from the beginning. The conclusion is not that the galaxy is empty. It is stranger and sadder than that. So let us close the loop. Start with biology, because the biology is where the argument becomes most vivid. Imagine we have somehow paid all of the energy costs we just walked through. Somehow, an advanced civilization has built a starship that can push a large payload to a substantial fraction of the speed of light, survive the dust bullets with layered shielding, and decelerate at the destination. Now they want to put living travelers on board. What has to happen for those travelers to survive the trip? The first problem is radiation. Deep space, outside the protective magnetic field of a planet, is bathed in cosmic radiation. High-energy particles arriving from all directions, most of them originating in supernova explosions across our galaxy, with the very highest energy particles arriving from far more distant sources. On Earth, we are shielded from most of this radiation by our atmosphere and our planetary magnetic field. In low Earth orbit, aboard the International Space Station, astronauts already receive a radiation dose many times higher than what they would receive on the surface. And this is a documented health concern even for missions lasting only months. Move outside Earth's magnetic field into interplanetary space, and the dose climbs further. Move into true interstellar space on a journey lasting decades or centuries, and the cumulative radiation exposure becomes lethal by orders of magnitude, unless you carry very heavy shielding. Shielding, of course, comes at a cost. Every kilogram of it is a kilogram you have to accelerate to cruising speed and decelerate at arrival, feeding directly into the energy problem we walked through earlier. So there is a direct, painful trade-off between how much shielding you can carry and how fast you can travel. More shielding means slower travel, which means longer transit time, which means more cumulative radiation exposure, which means you need even more shielding. The curves fight each other, and there is no clean solution. Even setting radiation aside, there's the problem of the body itself in low gravity. Everything we have learned from long-duration missions on the International Space Station tells us that the human body, when kept in microgravity for extended periods, deteriorates in ways we are only beginning to understand. Bone density drops, muscle mass shrinks, the cardiovascular system reorganizes itself in ways that make return to gravity dangerous. Eyesight changes, and not for the better. The immune system weakens, sleep patterns disrupt, and these are documented effects from missions lasting 6 months to a year. Extend the mission to decades or centuries, and there is no body of evidence to draw on because no one has ever survived that long in space. The extrapolations are grim. You could build a rotating spacecraft to simulate gravity, of course. This is a classic proposal, and it works in principle. But rotation is another engineering complexity, another failure mode, and another mass penalty. And rotation does nothing to help with radiation, closed-loop life support, or the psychological challenges of confinement. Speaking of life support, this is one of the most underappreciated problems in interstellar travel. On any journey lasting more than a few years, you cannot simply pack enough food, water, and air to last the whole way. The mass would be prohibitive. You have to close the loop. You have to build a self-sustaining ecosystem inside your spacecraft, one that grows food, recycles water, scrubs carbon dioxide, and regenerates oxygen, all without importing anything from outside. And it has to work for decades, or centuries, or millennia, without failing. Humanity has never built such a system. The largest attempts, most famously the Biosphere 2 experiment in Arizona in the 1990s, failed within a couple of years, with oxygen levels dropping, carbon dioxide rising, and ecosystems collapsing in ways the designers had not anticipated. The experiment was invaluable scientifically, precisely because it showed how much we do not yet know about building closed ecological systems that stay stable over time. Every real space station ever built, including the International Space Station, relies on regular resupply from Earth. None of them are truly closed. And scaling from resupplied from Earth to self-sustaining for 200 years with no outside help is not an incremental improvement. It is a categorically different engineering problem. Even if you solve the biological problems, radiation, gravity, life support, you still have the problem of the travelers themselves as social beings. A generation ship, one that carries not the original crew but their descendants across the decades and centuries, has to solve the problem of how to maintain a functioning society across many generations, in a confined space, with no way to expand, no external stimulus, and no way to abort the mission. Historical analogies are grim. Isolated human communities, even under much better conditions than a spacecraft could offer, have often collapsed into conflict, hierarchy failure, or ideological drift within a few generations. The idea that 100 or 1,000 people can maintain a stable, functioning, mission-focused society for 10 generations while sealed inside some metal shell, traveling through the dark, is a hypothesis with no empirical support and considerable reason for skepticism. I want to pause on the psychological dimension for a moment, because it is not just a science fictional worry. There is a real body of research on what happens to human beings in extreme isolation for extended periods, and the findings are not encouraging for anyone planning a multi-generational voyage. The most relevant studies come from Antarctic winter overstations, where small crews spend the polar winter completely cut off from the outside world for 6 to 9 months at a time. Even in these relatively short deployments, in stations with regular radio contact and the knowledge that rescue is theoretically possible within a season, researchers have documented a consistent pattern of psychological deterioration. The condition is well known enough in the polar science community that it has its own informal name: winter over syndrome. It manifests as depression, insomnia, cognitive impairment, interpersonal conflict, and in severe cases, symptoms resembling what psychiatrists call fugue states, And this is with fully volunteer, screened, professionally supported crews of well-adjusted adults in a mission lasting less than a year. Extend the analog. Long-duration analog habitats, including the HIC station on the slopes of Mauna Loa, which has run missions of up to a year, emphasize how quickly small group dynamics can turn corrosive under isolation. Submarine crews on extended patrols show similar patterns, mitigated only by the knowledge that the patrol will end. The most disturbing findings come from the longer studies. The Mars 500 experiment run by the Russian and European space agencies, which sealed a crew of 6 inside a mock-up spacecraft for 520 days, and documented sleep disruption, motivation collapse, and social withdrawal that worsened over the course of the mission. None of these are analogues to a multi-generational interstellar voyage. They are analogues to the first year of one. The findings do not tell us that generation ships are impossible, but they do tell us that the human mind is not built for the kind of long-term confinement that such missions would require. Any civilization considering such a mission would have to either engineer their travelers into something quite different from ordinary members of their species, or accept a high probability of mission failure through psychological collapse long before the destination is reached. This is not a problem you can solve with better engineering. It is a problem rooted in what minds do when they are cut off from their ordinary sources of stimulation, meaning, and social connection. An advanced civilization might have psychological technologies we cannot imagine, but the fundamental fragility of consciousness under prolonged extreme isolation is not obviously something that intelligence outgrows. The alternative is suspended animation. Some form of hibernation, cryogenic freezing, or induced metabolic slowdown that lets the travelers sleep through the journey and wake up at the destination. This is a staple of science fiction, and it is not obviously forbidden by physics, but it is deeply unsolved in biology. No mammal has ever been successfully frozen and revived. Some small animals, certain frogs, some insects, tardigrades, can survive extreme cold or dehydration through natural mechanisms. But scaling those mechanisms up to a human-sized organism with a complex nervous system is speculative at best. And even if we solve the freezing and thawing problems, we would still need equipment on the spacecraft that reliably maintains the sleepers for the entire journey, without failure, without power interruption, without any of the countless small malfunctions that accumulate in complex machinery over centuries. So biological travel is not just difficult, it is difficult in a compounding way, where each problem interacts with every other problem, and solving one usually makes another one worse. Heavy shielding fights against fast travel, rotating gravity fights against structural simplicity, closed life support fights against the possibility of failure. Generation ships fight against social stability. Suspended animation fights against the reliability of long-duration systems. Every direction you look, there is another wall. Now, let us come to the machines. If biological travel is nearly impossible, then perhaps the natural conclusion is that any interstellar civilization would send probes instead. Autonomous machines, self-repairing systems, perhaps even self-replicating ones. The famous von Neumann probes that so many discussions of the Fermi question return to. A single such probe, if it could be built, could arrive at a target star system, harvest local raw materials, build copies of itself, and send those copies onward to further stars. Given enough time, even at slow, sub-relativistic speeds, a fleet of von Neumann probes could explore an entire galaxy in a few million years. which is a blink of an eye compared to the age of the Milky Way. This argument is one of the strongest versions of the traditional Fermi paradox. If self-replicating probes are possible, then even one civilization anywhere in the galaxy's history could have filled the Milky Way with probes by now. And since we do not see any evidence of such probes in our solar system, no strange machines on the moon, no artifacts in the asteroid belt, no ancient signals from something parked at a Lagrange point, the argument goes that either the probes do not exist, or the civilizations that would have built them do not exist, or something else is going on. Before I complicate it, let me lay out just how demanding the von Neumann probe concept actually is when you examine the engineering closely. Because the argument that any civilization could have filled the galaxy with self-replicating probes by now assumes that such probes are possible in the first place, and this is worth interrogating. A functional, self-replicating probe has to do something no machine humanity has ever built has come close to doing. It has to arrive at an alien star system, identify usable raw materials without prior knowledge of what that system contains, mine and refine those materials autonomously, manufacture every component of a duplicate probe, including its own manufacturing equipment, assemble the copies, program them, launch them at new targets, and do all of this without any error that accumulates across generations of copies. That last point is more important than it first sounds. Every time you copy something complex, small errors creep in. In biology, this is what mutation is. The accumulated small failures of the replication process. Life handles this through error-correcting mechanisms that themselves evolved over billions of years of selection. A machine copying itself does not have that. Any error in the manufacturing process gets faithfully reproduced in the next generation, and errors accumulate exponentially. After 100 generations of copying, the descendants of your original probe may be so different from the original that they no longer function correctly, or worse, function in ways the designers never intended. The problem gets worse when you consider that the probe has to be robust to encountering star systems it was not designed for. Some star systems have plenty of accessible metals, some do not. Some have easy access to volatiles like water and organic compounds, some do not. A truly universal self-replicating probe has to be able to build itself from a wide range of raw materials, which means carrying either a very general-purpose manufacturing capability or a great deal of specialized equipment. Both options add mass, complexity, and failure modes. And even if you solve all of this, you still face the same fundamental problem we have been discussing all night. Each probe still has to cross interstellar distances, still has to pay the energy cost, still has to survive the dust bullets, still has to decelerate at the destination. Making them self-replicating does not repeal the physics. It just distributes the cost across many generations of machines, each of which faces the same crossing. A civilization that has genuinely solved all of these problems could indeed fill a galaxy with probes. But solving all of them is not a small ask. It's a suite of engineering achievements, each of which is on the frontier of what physics allows. The absence of von Neumann probes in our solar system may not mean that no civilization tried. It may mean that even for civilizations that tried, the project was harder than the traditional Fermi argument gives credit for, and less rewarding than the effort required. But I want to complicate this argument in a way that connects to everything we have been discussing tonight. Because even for machines, the situation is not as easy as it first appears. Machines do not eat, but they degrade. Every material we know of accumulates damage over time. Metal fatigues. Electronics suffer from radiation damage, the cumulative effect of high-energy particles knocking atoms out of place inside integrated circuits. Optics get scratched by dust impacts. Lubricants dry out. Batteries lose capacity. Even nuclear power sources decay on their own schedule, dropping their output steadily over the decades. A spacecraft that has to function for 100 years in deep space is not a mildly harder engineering problem than one that has to function for 10 years. It is a categorically different problem, because everything that is a minor concern over 10 years becomes a mission-ending concern over 100. An advanced civilization can build much more durable machines than we can. They can design for self-repair, build redundant systems, and use materials engineered at atomic scales to resist damage. These are not violations of physics. They are difficult engineering problems that a mature civilization might solve. But even so, sending a probe across interstellar distances is not free. Everything we said about the physics earlier still applies. Machines do not exempt themselves from the energy war, the dust environment, or the arrival problem. And on top of the physics, they carry their own peculiar burdens. The long, slow, cumulative degradation of the interstellar medium acting on materials that have to keep functioning for far longer than anything humanity has ever built to run. And it still requires the launching civilization to wait. Decades, centuries, sometimes millennia, before any results come back. Which brings us to the question that I think is the most important question in this entire story, and the one that most naturally leads to the conclusion I want to arrive at. Why would an advanced civilization do it? I do not mean that as a rhetorical challenge. I mean it as a serious engineering and economic question. Think about it from the perspective of a mature civilization. They have solved the observation problem. They have built enormous telescopes, either in their home system or in nearby space, that let them read the atmospheres of planets throughout their local neighborhood. They can detect oxygen, they can detect methane, they can detect industrial pollutants, they can detect the seasonal changes in vegetation. They can, in the limit, essentially watch a planet like Earth almost as if they were in orbit around it. What would a physical probe add to that? A little more resolution, perhaps? Some measurements that cannot be made from a distance? Samples of the atmosphere? Close-up images of the surface? Perhaps direct measurement of chemistry at the ground level? These are scientifically valuable, but not overwhelmingly more valuable than what remote observation delivers. And they come at a cost that, as we have seen, is astronomically higher than the cost of observation. The economics keep pointing the same direction. Every generation of better telescopes shrinks the marginal value of a physical probe. Every advance in remote sensing makes the trip look less worth taking. Observation improves, travel does not, and the gap between them widens with every century a civilization spends developing. And that ratio does not improve as a civilization becomes more advanced. If anything, it gets worse, because better telescopes reduce the marginal benefit of physical presence while the energy cost of physical travel stays anchored to the laws of physics. Now, consider a further question. What does a civilization actually want to do with the information it gathers about other worlds? If the goal is scientific, understand how planets form, how life arises, how civilizations develop, then observation gets you most of what you need, and the marginal benefit of physical visitation is small. If the goal is contact, actually communicate with the other civilization, then signals are cheap, work reliably, and require no ships at all. Even if signals take decades or centuries to arrive, they are still faster and cheaper than any physical mission. If the goal is colonization or resource extraction, then the calculation is different, but the economics look grim. There are no known resources in another star system that are not more cheaply available in your own. And colonization, moving a viable population of your species across the interstellar gulf and establishing them on a foreign world, inherits every biological problem we discussed, multiplied by the scale of the undertaking. So here is where I want to bring the argument to its point. There is a plausible scenario, consistent with everything we know about physics, in which the galaxy contains many advanced civilizations. Perhaps thousands, perhaps more. They have detected each other's atmospheres. They have read each other's biosignatures. Some of them may have exchanged signals, patient, decade-long, century-long conversations conducted across the dark. They know they are not alone, and they have all independently arrived at roughly the same conclusion about physical travel. That the energy cost is enormous, that the dust bullets are hostile, that the braking problem doubles every budget, that the biology is fragile beyond the point of survival, that the machines that could make the journey deliver information only marginally better than what a good telescope can gather from home, that the whole exercise for any goal a mature civilization might have is not worth the cost. The result is a galaxy where seeing is normal and traveling is rare, or never done at all. A galaxy where civilizations are aware of each other in the way that people on opposite sides of an ocean might be aware of each other's lights, visible, real, confirmed to exist, and physically unreachable. A galaxy of watchers and no visitors. I want to be careful about what I am and am not claiming. I am not claiming this scenario is proven. I am not claiming physical interstellar travel is absolutely impossible. There are propulsion concepts and engineering approaches that could shift the calculations. There are edge cases where a patient civilization might send a slow probe across the dark for reasons we cannot easily understand. The universe is large and strange, and I would not bet against every conceivable exception. But I am claiming that this scenario is plausible. It is consistent with everything we know about physics. It is consistent with the observed silence. The fact that we have not, despite decades of searching, found any clear evidence of visitors in our solar system or of active civilizations reaching towards us. It is consistent with the asymmetry between observation and travel that grows more pronounced with technological maturity. And it is a scenario that is not usually presented in popular discussions of the Fermi question, which tend to jump straight from they exist to so where are they, without pausing on the possibility that they exist and they never come here, might both be true at the same time, permanently. This is the strange middle ground that I've been trying to point toward all night. Not the empty galaxy of one set of answers. Not the visited Earth of another set. Something in between. A galaxy full of neighbors who know we are here and cannot come. Let me try to describe what that feels like, because I think the feeling matters. If the traditional lonely galaxy scenario is true, if we really are the only technological civilization anywhere in the Milky Way, then the burden that falls on our species is enormous, but it is at least a familiar kind of burden. We're alone, we are unique, and everything that consciousness has produced in this galaxy has been produced here. That is a heavy weight, but it is a weight we can imagine carrying. Alternatively, if the traditional crowded galaxy scenario is true, and civilizations do routinely arrive at each other's doorsteps, then our future is one of eventual contact. For better or worse, we will meet someone, and everything after that meeting will be shaped by it. But the scenario I have been walking you through is neither of those. It is a galaxy in which we might be one of many, in which our existence might be quietly known to distant observers, and in which the meeting will never happen. Not because anyone has forbidden it, not because of malice, not because we are being hidden or protected or watched from behind some cosmic curtain, but because the ocean between us and them is simply too wide, too deep, and too full of teeth for anyone to cross. There is a specific quality to that kind of isolation that I want you to sit with for a moment. It is not the isolation of being alone. It is the isolation of being seen from a distance and unable to be reached. It is the loneliness of a shore that faces a lit coast across an uncrossable sea. Both parties know the other exists. Both parties can watch the other. Neither will ever walk on the other's ground. For me, and I want to be careful here because I know this crosses into personal reflection, there is something both frightening and consoling about this possibility. Frightening because it suggests that the universe may be structured in such a way that intelligence, however common, is permanently fragmented into isolated islands, unable to build the connections that we intuitively expect intelligence to build. Consoling, because it suggests that the silence we hear when we listen is not evidence that we are alone in a hostile, empty cosmos. It is potentially evidence that we are in a galaxy full of company, none of which can reach us. Those are very different silences. They should feel different. There is also a practical dimension to this, which I think matters for how our species thinks about its future. If interstellar travel is as hard as the physics suggests, then the choices we make right now on this planet matter more than any narrative of eventual arrival gives us credit for. If nobody is coming, then the future of consciousness in this corner of the galaxy is something we ourselves are responsible for. Not because we won the cosmic lottery of being alone, but because we are the only intelligence within our reach. And our reach is much smaller than the traditional science-fictional imagination has led us to expect. This does not close the door on interstellar exploration. It does not close the door on eventually sending small, brave probes to nearby stars. Projects like Breakthrough Starshot might well succeed, in modest form, within this century or the next. It does not close the door on receiving signals from other civilizations, or on someday sending our own. It just repositions the entire question. It says that our future, and the future of any intelligence we know about, is largely a future of local activity, of doing what we can within the reach of our physical presence, of building signals and telescopes for the long-distance conversations, and of accepting, with whatever grace we can muster, that the meaningful acts of interstellar civilization may be mostly acts of observation, not acts of travel. Let me close with the image we began with, because I think it holds up under all of the physics we have walked through together tonight. We are standing on a shore. Across an enormous ocean, we can see the lights of another city, real, confirmed, undeniable. We know they are people. We know they see us too. On clear nights, we can even watch their lights blink on and off in patterns that suggest ordinary lives being lived. ordinary hopes and struggles, ordinary joys and griefs. We could send messages by lantern flash across the water. We could receive their lantern flashes in return. Over years, we might build a slow conversation, but we will never cross the water. The ocean is too wide, too deep, too full of storms, and too full of things that would sink any boat we know how to build. Our best ships would be lost before they reached the other shore. Our sturdiest travelers would not survive the crossing. And even if one of us built a marvelous vessel that could make the journey would take longer than any of us would live to see finished. And the vessel would return, if it returned at all, to a shore where no one remembered why it had been sent. So we live on our shore, and they live on theirs, and the sea between us stays uncrossed. That is not a story of an empty world. It is not a story of a hostile world. It is a story of a world where knowing and going are two different things, and where knowing is enough to change everything, and where going may never happen at all. This is the possibility I wanted to sit with you tonight. Not because it is proven, not because it is certain, but because it is what a careful walk through the physics keeps pointing toward. And because, if it is true, it changes how we should feel when we look up at a silent sky and wonder whether anyone is out there. The silence might not be empty. It might be the sound of a galaxy full of neighbors, watching each other across the dark, unable to close the distance, doing what any of us would do in their place, living where they are, being what they are, and knowing, with as much peace as they can find, that they are not alone, even if they will never meet the ones they know are there.